Ladies and gentlemen, welcome back to Lesson 11 in Group Theory. This lesson, we will explore something called commutativity in groups. We know what commutativity is. If two elements A and B are commutative, then they hold the property A times B is equal to B times A. And we've seen that a group is called abelian if all of its elements are commutative. But what if we don't have an abelian group? Do we just give up? No, we will try and look for elements in the group which are commutative with every other element in the group. We will take these elements and we will form subsets of the group, special subsets, which we call the center, the centralizer, and the normalizer. So with that in mind, this topic is about not only finding abelian groups, but finding the abelianity in a group, finding the elements which are commutative inside a group, which is not necessarily commutative. So with that in mind, let's jump into it. Let us now define what the center of a group is. The center of G, denoted by ZG, is equal to all the elements G and G, so the set containing the elements G and G, such that A times G is equal to G times A. And that is true for all A in G. So in words, we say that this is the set containing the elements in G that commute with all the elements in G. And another way to express this definition, which is also equivalent to the first one, is by noticing that we can apply G inverse on both sides, or we can apply A inverse on both sides, and we can get different interpretations of this definition. So if we apply, for example, A inverse on both sides, like that, then we find that this is the set of all G and G, such that A, G, A inverse is equal to G for all A in G. So we find that the conjugate, if you remember the term conjugate from our lesson in symmetric groups, that's lesson 5, this is the conjugate of G by A. The conjugate of G by A is exactly equal to G no matter what A was in the entire group. So this is also another definition for the center. Notice that the center is the most restrictive set that we're going to encounter today, because the more we go through the lesson, we're going to be coming through definitions like the center, the centralizer, and the normalizer. And each definition will be less restrictive than the last, because the center here has the condition of commutativity for all the elements on the group. But in a centralizer, that is not necessarily the case. And for a normalizer, it is not even necessary to have a strictly commutative property. And we will see that in a minute. But just to remember that the center is really small. It's included inside the centralizer, which itself is included inside the normalizer, which itself is included inside G. So it's sort of multiple shells, multiple layers of what we're gonna be discussing today, starting from the innermost layer, which is the center. If G is abelian, so a special case where the group is abelian, that means it's commutative. So A times B is equal to B times A for all A and B in G. We have that the center of G is equal to all of G itself, because no matter what G we use here, we have that AG is equal to GA for all A in G. So if you pick any element in G, that element will commute with all of the other elements in G. So technically, the center would be equal to all of G. And that's a pretty good way to find out if G is abelian or not, just to calculate the center and see if it gives all of G or not. To understand the notion of centers better, we're going to be taking the center of groups that you've already seen before, such as the dihedral group, the symmetric group, and the quaternion group, which we've seen in lessons 4, 5, and 6. So to start with, we'll take the center when n is bigger than or equal to 3 of D to N, the dihedral group of sides at least 3. So first of all, we need to list what D to N is, give us an idea of what can we take for the center. And the elements are the identity symmetry, the rotations, and all the symmetries of the form SR to the K, where K is a number between 1 and n minus 1. So to look at the center, we need to look at the elements which commute with all of the elements of D to N. So let's take a random element SR to the K for some K that we don't know of. And let's see if it commutes with any element in D to N, including the element R. So let's take it with the element R, and let's see that this is equal to that. So R times that element is equal to that element times R. So the left-hand side will be equal to RS times R to the K. The right-hand side will be S times RK times R. Okay? Now, the left-hand side will be equal to SR to the minus 1 times RK, and the right-hand side will be SRK plus 1. Left-hand side will be equal to SRK minus 1, and the right-hand side is again SRK plus 1. So, if we want for this to be a valid operation, a valid relation between these two elements, then we will have to have that these two things are equal. So SRK minus 1 is equal to SRK plus 1. And now, simplifying, we get RK, R minus 1, is equal to RK, R. Simplifying again, we get that R is equal to R inverse. In other words, a single rotation clockwise is equal to a single rotation counterclockwise. So for what n is this equality a valid equality? Well, for n is equal to 1, we have a single point. The vertex is a single point, and no matter what rotation we take, it's a very trivial example, and it will be valid. For n is equal to 2, we will get two vertices and an edge between them making a line. So if we take a clockwise rotation, it is the same as taking a counterclockwise rotation, because in either rotations they will just swap the vertices places apart. Okay? So what about for n is equal to 3, or n is bigger than or equal to 3? Well, for n is equal to 3, we would have a triangle, and we've seen that R of a triangle is not equal to R inverse of a triangle. And that is true for n equals 3, n equals 4, n equals 5, for all n bigger than or equal to 3. So we conclude that this equality is true if and only if n is equal to 1 or n is equal to 2. And since we have assumed that n is at least 3, we know that this equality is not true. Therefore, this is not true, and we can go back, trace all the steps back to the first one here, and say that R times this is not equal to SR to the K times R. Therefore, saying that for n bigger than or equal to 3, SR to the K is not a member of the center, since it does not commute with R. And we can say in the same vein that R is not a member of the center, because it does not commute with SR to the K for any K between 1 and n minus 1. So we've just hit two birds with one stone by excluding the cases of SR to the K for all K between 1 and n minus 1, and of R, basically. So this just leaves us the identity. So if n is odd, I will get to that in a minute, why I specified n to be odd. If n is odd, the center of d to n is just equal to the identity, symmetry. No other element commutes with all of the elements in the group. This is the only one. If n is even, what happens? If n is even, then we can say, actually n is even if and only if n is equal to 2k, 2 times k, for some k an integer. And this, of course, is if and only if n is equal to k plus k, and that's if and only if n minus k is equal to k. And this seems a bit artificial, but you'll see in a minute why this is very useful. So if we take r to the power n minus k, this would mean r to the n minus k would be equal to r to the k, right? And we know for a fact that r to the n is the same as the identity. So this is if and only if r to the minus k is equal to r to the k. And if we apply s on both sides, we would have sr to the minus k is equal to srk. And now we will use a property we've seen in permutations, in algebra of permutations, to say r to the k times s is equal to sr to the k by flipping s and r to the minus k and changing the sign of the power of r. So we've just seen that r to the k commutes with s. And so we're naturally inclined to say that this means that r to the k is an element of z d to n, because already r to the k commutes with any rotation or any multiple of rotations that we have. Because rotations, if we combine them together using exponent laws, we can just separate them. For example, r to the a, r to the b is equal to r to the a plus b equals r to the b plus a equals r to the b, r to the a. So it doesn't matter in which order we take our rotations in, they're always commutative with each other. Our only worry was commuting it with s. But here we see that if n is even, then we have r to the k times s is equal to s times r to the k. So no worries there. So we have that, and we're inclined to say also that s is an element n z d to n. But is that the case? We need to investigate that further. What if k is equal to 1? So SR is equal to RS? Well, no, not really. We've already seen that SR is equal to R minus 1S. So if we cancel S on both sides of the equation, we will get that R minus 1 is equal to R. And we've already seen that this is if and only if n is equal to 1 or n is equal to 2. But we don't have that case here. We have n is bigger than or equal to 3. So S cannot be a member of the center, which leaves us with the only possibility, other than the identity, of course, that R to the k is a member of Z d to n. So if n is even, then Z d to n, the center, is the set containing 1, the identity, and R to the k. But k, what is k here? What did we say it was? Well, we said it was n is equal to 2 times k, so k is equal to n over 2. So that is what I'm going to write here, n over 2. And that is all the elements of the center of d to n if n is even. And if n is odd, then we don't even have that element, and we're only left with the identity element in our center. Thus completing this example for the dihedral group. Let us now look at the center of the quaternion group. To deduce what is the center of that, we would have to list again the group of the quaternions to be the identity minus 1, I minus I, j minus j, and k minus k, where, if you remember, I square and j square and k square are equal to minus 1. So they're all square roots of minus 1, and k is equal to I times j, and I times j is equal to minus j times I. Okay? So what is the center of Q8? Well, the identity is always the case. Always, identity times any element is equal to that element times the identity. So we can just simply say ZQ8 contains the identity. Okay, what else? Minus 1. Is it a candidate? Of course. Minus 1 is a real number. Multiplying a real number by any of these will get you a commutative property multiplication. So minus 1 times I is equal to I times minus 1, which is equal to minus I. And you can just experiment with that with any of the other elements to get the same result. So we can add minus 1 to the center of Q8. Minus 1 commutes with all of the elements of Q8, therefore minus 1 is an element of the center. Okay, what about ijk? What about their inverses, minus I, minus j, minus k? Are they part of the center? Okay, so we know that k and minus k are two different elements, right? We cannot say that k is equal to minus k. Then there would be no point in listing them like that. Then we would say they're not equal. But k is equal to I times j, and minus k is equal to minus I times j. And I times j is equal to minus j times I, and that is just equal to j times I. And we've said that k is not equal to minus k, so we can say that ij is not equal to ji, huh? So I does not commute with j, therefore I does not belong in the center, because it does not commute with a single element, which is j. It needs to commute with all of the elements. So because it does not commute with one, it's already excluded. And with the same logic, we say that j is not an element of the center. And with the same logic, we can say that k is not an element of the center, because k is simply I times j. It depends on I times I and j. So because I, j, and k are not in the center, it's reasonable to say that minus I, minus j, and minus k are not in the center as well, because, well, they're just minus I, which is minus 1 times I. So none of these elements here belong to the center of Q8. So the center of Q8 only contains 1 and minus 1. All the other elements do not commute at one point or another with some element in the group, which means that this is the center of Q8. Okay, let us look now into the center of Sn, the symmetric group, the group of permutations of a set, and we will see immediately that if n is equal to 1 or 2, we have a trivial case here. So if n is equal to 1 or 2, we have that z of Sn, so if n is equal to 1 or n is equal to 2, z of Sn immediately equals all of Sn. You can see that for yourself. Try it out. It's very easy. N is equal to 2, we have two elements. That means we have two permutations, the identity permutation and the one where it swaps the elements. Each of those commutes with all the elements in the group. Therefore, z of Sn is Sn, and Sn would be abelian. Okay, what about S3, S4, S5, Sn bigger than 3? So what if n is greater than or equal to 3? Well, let E be the set that contains 1, 2, 3, all the way to n, where n is bigger than or equal to 3, of course. So at least 3 elements in the set E. So if we let sigma to be the permutation containing only 1, 2, so the 2 cycle 1, 2, so it swaps 1 and 2 together, then we can say let tau be a permutation that lies in the center of Sn. Okay, what can we say about tau then? Because if an element is in the center, that means it commutes with all of the elements in Sn. In particular, it commutes with sigma. So tau sigma is equal to sigma tau, commutative. But then this leaves us two choices. Either two choices, first case, second case, one of which must be true. Either sigma and tau are disjoint. So if they're disjoint, that means that tau does not contain 1 and 2 in its cycle decomposition, so tau fixes 1 and 2, or sigma and tau are not disjoint, but then tau has to swap 1 and 2. So tau swaps 1 and 2. Because remember, in symmetric groups, we've said that disjoint cycles are commutative, which is why we ended up deducing these two possibilities, where one of which is true. Now, we can repeat the same sort of argument, but not with sigma, with another two-cycle. Let sigma prime be equal to the two-cycle that swaps 2 and 3. Because remember, E is a set that contains at least 3 elements, so we can have 2 and 3 as well. So tau sigma prime is equal to, you guessed it, sigma prime tau, leaving us two possibilities again. One, sigma and tau, sigma prime and tau are disjoint. This means that tau fixes 2 and 3. The second one being that tau swaps 2 and 3. Okay, let's see what we get when we combine these logical possibilities together. We know for a fact that either one of these is true and that either one of these is true. Let us assume that tau swaps 1 and 2 together. So let us assume this is true and this is not true. What do we get? In the other case, since tau swaps 1 and 2 together, we know that tau does not swap 2 and 3 because 2 is already swapped to 1. So this is not true. But this means this has to be true. But is it? Here it says tau fixes 2 and 3. But we've said that tau swaps 1 and 2. So it swaps 2. So 2 is not really fixed, is it? So this is also not true. So this is a logical impossibility because we've assumed that either one of which has to be true. So this leads to a contradiction which we arrived at assuming that tau swaps 1 and 2, which means that this forces us to say that is not the case. And the other has to be the correct case. Now let us see what happens in that case. If tau fixes 1 and 2, then it cannot swap 2 and 3 because 2 is already fixed. So it eliminates this possibility. And then this leaves us only with the other possibility where tau fixes 2 and 3. So this leaves us with the conclusion that tau fixes 1, 2, and 3. 1, 2, and 3. Now, can we repeat this process? If we had, let's say, a fourth element, you bet. We can have sigma double prime to be the two-cycle containing 3 and 4. And then we can have tau fixes, so 3 and 4, and then sigma triple prime to be 4 and 5, and then all the way to n minus 1 n, and then now tau fixes 1, fixes 2, 3, 4, all the way to n. So we arrive at the conclusion that tau fixes all of the elements in E. Therefore, tau is exactly the identity permutation. So, just by assuming that tau is an element in the center of Sn, we have arrived at the conclusion that tau must be the identity permutation, therefore concluding that the center of Sn is exactly equal to the set containing just the identity permutation. So either when n is equal to 1, n equal to 2, the center of Sn is the entirety of Sn, or when n is greater than or equal to 3, the center is just the identity. There is no in between. It's a very dramatic center. It's either nothing or everything. And that completes the example for Sn. Okay, so we've seen that a center contains the elements which are commutative with all of the elements in the group G. But what if we don't necessarily want the element to be commutative to all of the elements? What if we want the element to be commutative to a set of elements that we want that is inside G? And this is where the centralizer comes in. So if G is a group and A a subset of G, the centralizer of A in G is given by CGA, this is the group and this is the subset, to be equal to the set of elements in G that are commutative with all the elements A in A. So again, this is the set of elements that are commutative with all of the elements in not all of G, but just the subset A of G. And we can vary A as we like. A could be any special subset we like. It could be all of G, it could be one element, it could be two elements, whatever. And this can be equal to, equivalently, G in G, such that AGA inverse is equal to G for all A in A. We can play with it as we like. We can even say GA G inverse is equal to A by just moving around stuff. I leave that up to you as an exercise to verify the validity of what I'm saying. So in particular, if we take the center, well, that's just the case when A is equal to G, which is CGG. So that instead of saying A here, we should just be saying all of G. So let us now move to proposition 1, which tells us that not only the centralizer is a subset of G, but also a subgroup of G, no matter what A was. So to prove this proposition, we would need to prove normally what a subgroup is. So the first condition would be to prove that it's not empty. So CGA is not empty since the identity is found in CGA, because the identity naturally commutes with all of the elements in A, in G even. The second thing is that if G1 and G2 are two elements, arbitrary elements in CGA, and let A be any element in A, arbitrarily chosen, then prove that G1, G2 inverse is in CGA as well. And this is a sufficient and necessary condition for subgroups, as we've already seen in lesson 9. So to do that, we're going to use one of those definitions here of conjugacy. In fact, we'll be using this one here, and instead of G, we'll be using G1, G2 inverse. So G1, G2 inverse times A times the inverse of G1, G2 inverse. And I want all of that just to equal A at the end. If I succeed in doing that, I would have finished my proof. So this is equal to G1, G2 inverse times A times G2 inverse inverse, G1 inverse, and this is equal to G1, G2 inverse, A, G2, G1 inverse. And now let us group the elements in the middle. And we know that this here is equal to A. Why is that? Well, remember that G2 is in the centralizer of A and G. So we can say since G2 is in the centralizer, we have that G2 A, G2 inverse is equal to A, and applying the G2 inverse on both sides of the equation, we will have that G2 inverse is here, and applying G2 on both sides of the equation, we will have this relation like that. So this is exactly what we get. So this is equal to G1 A, G1 inverse. But this, notice, because G1 is in the centralizer as well, we can just say that this is equal to A. This is since G1 is in the centralizer of A and G. So we've just proven that this beast here is all equal to A. Therefore, G1, G2 inverse is a member in the centralizer, completing our proof. Okay, it's time for some small notation and some remarks before we get into the examples. One notation is that if A contains a single element, A, we're going to write CG of A instead of CG of the set containing A. That's all for that notation. And the small remark is, because the centralizer is a subgroup, we know that it is closed under the operation, the group operation, and under the inverses. So we can say that A to the power n is an element of CGA for all n in Z. If you want to explore this idea further, I encourage you to work at it and prove that explicitly. So for the examples, we have that CQ8I. So basically, the centralizer of the element I in the group Q8. So basically, all of the elements which are commutative with I. And all of the elements which are commutative with I are plus and minus 1 and plus and minus I. J and K, minus J, minus K are not commutative with I. So this is the centralizer of I in Q8. What about the centralizer of the set containing 1 R, R square, R cube in the group D8, the dihedral group of a square? So here we have that this is equal to, so what are the elements here that are commutative with all of the elements in this set? And these are exactly 1, R, R square, and R3. There are no other elements that are commutative with all of these elements here. S, SR, SR square, SR3 are not commutative with these elements. So this is just that. And we can simply say this is equal to the set generated by R, because all of these are multiples of R, and this can be written as CD8 of R. In other words, the centralizer of R in D8 is equal to the centralizer of the whole set generated by R in D8. And last example is the centralizer of the center. In other words, all the elements that are commutative with the elements in the center. Well, that's equal to G, because remember, the elements in the center are commutative with all of the elements in the group. So that's why I write G here. I'll give you some time to reflect on it, and I encourage you to work at it slowly and get used to the notation and definitions of these interesting facts. Okay, now that we've seen the definitions and examples on centers and centralizers, it is time finally to talk about normalizers. So what happens here? Well, in normalizers, what we're doing is we're loosening it up a little bit. We're loosening up the restrictions that we're putting on centralizers. Remember, for centralizers, these are all the elements in the group G such that G A inverse is equal to G for any A in A. So a centralizer, essentially, if you had G in the centralizer, then we would have G inverse is equal to A for all A in A. Okay? However, in normalizers, we don't want to go that far. We don't want to go that far to say that the conjugation is equal to the element. We just want to be able to say that G inverse is equal to some A1 in A. Not necessarily the same A that is in A. Okay, so that is the subtle difference. So we're not as restrictive as in the centralizer. We just want to be able to get an element that is inside A. So we just want to say that G inverse is going to be an element in A, not necessarily equal to A. Okay? So that is the definition of the normalizer. Formally speaking, if G is a group and A is a subset of G, the normalizer of A in G is denoted by NGA, and that is equal to the elements G in G such that G times the set A is equal to the set A times G. Well, what do I mean by that? In terms that we understand in set theory. So when I multiply an element by a set, essentially what I'm getting is a new set, which is G times A1, G times A2, G times A3, and so on. For all the elements in A, what I do is I multiply G on the left for all the elements in A, and this is the set I get, which I call GA. And this I claim to be equal to AG. So basically, A1 times G, A2 times G, A3 times G, and so on. Basically claiming that these two sets are equal. So basically, if I take a G times A3, for example, this one here, I am sure to find an element here. So there exists a K such that G times A3 is equal to AK times G. Essentially, that's what I'm saying. And the thing is true from the opposite direction. So here, essentially, instead of saying G times A is equal to A times G for every element A, we're having G times the whole set is equal to the whole set times G. We're being less restrictive in that sense. And if we use our basic manipulations that we used before, we can say the normalizer is also all the G's such that G inverse is equal to A. Essentially saying that if you take any element A in A, so G inverse is equal to the set of G inverses where A is an element in A. The set of all the conjugates of A for all A in A by G. So we're just saying that this set of conjugates is equal to A. So if you take any elements in A, you apply the conjugate, you're sure to bound in A. It is closed under conjugates. And A final way to say it would be to say this is all the elements G in G, such that G small a G inverse is an element in A for all A in A. So whereas before we used the set notation, this is a set, this here is just an element in a set. But all the three definitions are exactly the same. Let us now look at an example of a normalizer in the diagonal group D8. So what is the normalizer of the set containing 1, R, R square, R3 in the group D8? The normalizer, in fact, in this case, is the whole group D8. Whereas before, when we took the centralizer, if you remember, the centralizer of the same exact set, I'm just going to write the subgroup generated by R, was just itself. The normalizer is bigger. It's actually the entire group D8. And why is that? Because we find out that if you take any element, so take for example any element in D8 and you apply the conjugation, you'll find that you are still in 1R, R square, R3. You're still in that set. So let's do that. Let's see. Here, n D8 of the subgroup generated by R, by definition, is equal to all the G in D8, such that G A G inverse is an element in R for all A in R. Okay, that's the formal definition of the normalizer. It's when you take the conjugate and you're still inside the subgroup generated by R, no matter what generation A in R that you use. Okay, so we can be arbitrary in choosing our multiple of R by saying R to some power K. So R to K for some power K is going to land us in here. So RK is in the subgroup generated by R. And now we want to see what happens when you do G A G inverse for any G that is in D8. So we know that D8 is generated by S and R, and we know that the elements of D8 are of the form S R to the L, where L could be 0, 1, 2, all the way to n minus 1, right? So we can have SR to the L multiplied by our element R to the K, and then multiplied by the inverse of SR to the L. So this is exactly the conjugation of our element R to the K inside the subgroup generated by R by any element of the form SR to the L. Let us see what that gives us. So this gives us here, we're going to use some algebra properties to say this is SR to the L, R to the K, and the inverse applies on both here, inversing their order. We have R to the minus L and S to the minus 1. Now we know that this here is commutative, so we can cancel out the R to the L and R to the minus L. And we know that we're inversing the order of these two is going to switch the sign of the K here, giving us R to the minus K times S to the minus 1. Canceling these two, we end up with R to the minus K. But that is a multiple of R. It's a power of R. So it lies in the subgroup generated by R. So you can see that this conjugation of R to the K lands us also in some element that is inside the subgroup generated by R, even though it's not equal necessarily to R to the K, but it lands us to some element in the group, in the subgroup. So that is sufficient for us to say that SR to the L for any L from 0 to n minus 1 is an element in the normalizer of the subgroup, which says that essentially that the normalizer is everything. It's D8. So this was an example of the normalizer of the subgroup generated by R in D8. Now let's see the example of the normalizer of this set containing plus 1 minus 1 and plus I minus I in the group Q8. What would that give us? Well, I'm here to tell you that the normalizer here is also Q8, the entire group Q8. And how is that possible? We've seen before that the centralizer, if you remember, the centralizer in Q8 of I is simply the subgroup generated by I. It's just plus and minus 1 plus and minus I. It is not all of Q8, but here, since we're being less restrictive in our conditions, we can allow for more freedom. So it's Q8. How is that possible? Well, again, we take the definition of a normalizer. So NQ8 of the subgroup I, it is equal to all of the elements in Q8 such that G inverse is inside I, the subgroup of I, for all A in the subgroup of I. So if you want to take an arbitrary A, we got to take an arbitrary power of I. So I to the K. I to the K is an element in I. Okay? So we take I to the K and we have this here. We have the conjugation of an element with I. What will that give us? Well, what are the elements that are possible in Q8? We have I, we have minus I, we have J, minus J, K, minus K. So let us consider J and K and see what we get. So J times I to the K. Well, J I to the K and then the inverse of J. But the inverse of J, we know it is minus J. Okay? So we need to see what can we do about the K here. Well, the K can be 0, in which case I is equal to 1, but that's trivial. That's just the identity. The identity is always commutative, so we can commute and we're good. The conjugation is fine. What if K is equal to 1? Well, that's just I, right? What if K is equal to 2? Well, that's just minus 1. And 1 and minus 1 are trivially true to be in the normalizer. But the cases that are not trivial, which are K is equal to 1 or K is equal to 3, or maybe K is 5 or 7, or So it's going to be repeating itself. So K, the only non-trivial cases for K is either K is equal to 1 or K is equal to 3, in which case we have minus I, right? So let us consider both cases individually. We have here in the first case, J minus I, we get minus Ji times minus J. And we use one of the properties we know about quaternion groups to flip this and that and change their signs to have Ij times minus J. And this gives us just I times minus J squared. And minus J squared is equal to I times minus of minus 1, which is just equal to I. And I, of course, lies in the subgroup generated by I. So the good news is we already land in the subgroup of generated by I. And for the other case, we have that Ji is equal to minus Ij times minus J, of course. This equals to minus I times minus J squared, which is equal to minus I. And minus I is in fact an element of the subgroup generated by I. So even though j times minus I times minus j is not equal to minus I, it's equal to I. So if we were talking about centralizers, this would not be in the centralizer because the conjugate of minus I is not equal to minus I. The conjugate of I is not equal to I. They're not equal. However, they do give an element that is inside the subgroup that we're talking about, which is the subgroup generated by I. So as long as that condition is met, we can say that J is an element of the normalizer. Okay? So we've covered for J, and K can be done in the same way, and we can say that for K as well it works. We can say the same, it works for minus J, for minus K, and 1 and minus 1 are obviously trivial. So we can say the same for all of the elements of Q8, and we say that the normalizer is in fact the whole group Q8. So this thing where the normalizer is the whole group, this is a special thing. It is called a normal subgroup of Q8. And this, in fact, we will look into it later on this course. This is what a normal subgroup looks like. It's when the normalizer of that subgroup is the entire group. But that's a discussion for a later time. For now, just focus on what a normalizer is and how to prove that an element belongs to the normalizer of a given subset of the group. The last thing we're going to cover before wrapping up this lesson is proposition 2, telling us that for any subset A in G, we have that the normalizer of A in G is a subgroup of G. And the proof is left to you as an exercise because it is done in a very similar fashion to the proof done in proposition 1. So I highly recommend you give it a go. And the last thing to say is that if G is the entire group like that, then we have that the normalizer would be something like the second biggest. Afterwards comes the, so this is N, and then afterwards comes C, and then the smallest one would be the center, Z. I'm guessing this is why they would call it the center, because it is sort of the nucleus, the commutative nucleus, if you will, of G. So the center is the subgroup of the centralizer of A, which is a subgroup of the normalizer of A, which is a subgroup in turn of G. And with that, we finish today's lesson. If you've enjoyed, please like, subscribe, and share with your friends about these interesting topics. I will be posting much more videos talking about all kinds of stuff, including the normal subgroups, which I've mentioned earlier. So yeah, have a nice day.